A floppy disk, or diskette, is a disk storage medium composed of a disk of thin and flexible magnetic storage medium, sealed in a rectangular plastic carrier lined with fabric that removes dust particles. Floppy disks are read and written by a floppy disk drive. Floppy disks, initially as 8-inch media and later in 5 1/4 inch and 3 1/2 inch sizes, were a ubiquitous form of data storage and exchange from the mid-1970s well into the 2000s. By 2010, computer motherboards were rarely manufactured with floppy drive support. 3 1/2 inch floppy disks can be used with an external USB floppy disk drive, but USB drives for 5 1/4 inch, 8-inch and non-standard diskettes are rare or non-existent, and those formats must usually be handled by old equipment. While floppy disk drives still have some limited uses, especially with legacy industrial computer equipment, they have been superseded by data storage methods with much greater capacity, such as USB flash drives, portable external hard disk drives, optical disks, memory cards and computer networks. History. The earliest floppy disks, developed in the late 1960s, were 8 inches in diameter. They became commercially available in 1971. These disks and associated drives were produced and improved upon by IBM and other companies such as Memorex, Shugart Associates, and Burroughs Corporation. The phrase floppy disk appeared in print as early as 1970, and although in 1973 IBM announced its first media as Type 1 diskette, the industry continued to use the terms floppy disk, or floppy. In 1976, Shugart Associates introduced the first 5 1/4 inch FDD. By 1978 there were more than 10 manufacturers producing such FDDs. There were competing floppy disk formats, with hard and soft sector versions and encoding schemes such as FM, MFM and GCR. The 5 1/4 inch format displaced the 8-inch one for most applications, and the hard sector disk format disappeared. In 1984, IBM introduced the 1.2 MB dual-sided floppy disk along with its AT model. IBM started using the 720 KB double-density 3 1/2 inch micro-floppy disk on its convertible laptop computer in 1986 and the 1.44 MB high-density version with the PS/2 line in 1987. These disk drives could be added to older PC models. In 1988 IBM introduced a drive for 2.88 MB DSED diskettes in its top-of-the-line PS/2 models, but this was a commercial failure. Throughout the early 1980s, limitations of the 5 1/4 inch format became clear. Originally designed to be more practical than the 8-inch format, it was itself too large. As the quality of recording media grew, data could be stored in a smaller area. A number of solutions were developed, with drives at 2, 2A1 or 2, 3 and 3 1/2 inches offered by various companies. They all shared a number of advantages over the old format, including a rigid case with a sliding metal cover over the head slot, which helped protect the delicate magnetic medium from dust and damage, and a sliding write protection tab, which was far more practical than the adhesive tabs used with earlier disks. The large market share of the 5 1/4 inch format made it difficult for these new formats to gain significant market share. A variant on the Sony design, introduced in 1982 by a large number of manufacturers, was then rapidly adopted. By 1988 the 3 1/2 inch was outselling the 5 1/4 inch. By the end of the 1980s, the 5 1/4 inch discs had been superseded by the 3 1/2 inch discs. By the mid-1990s, the 5 1/4 inch drives had virtually disappeared as the 3 1/2 inch disc became the predominant floppy disk. The advantages of the 3 1/2 inch disc were its smaller size and its plastic case, which provided better protection from dirt and other environmental risks, while the 5 1/4 inch disc was available cheaper per piece throughout its history, usually with a price in the range of 1/3 to 2/3 of a 3 1/2 inch disc. Ubiquity. Floppy disks became ubiquitous in the 1980s and 1990s, and their use with personal computers to distribute software, transfer data, and create backups. Before hard disks became affordable, floppy disks were often used to store a computer's operating system. Most home computers had a primary OS and BASIC stored as ROM, with the option of loading a more advanced disk operating system from a floppy disk. By the early 1990s, the increasing software size meant large packages like Windows or Adobe Photoshop required a dozen disks or more. In 1996, there were an estimated 5 billion floppy disks in use. Then, distribution of larger packages was gradually replaced by CD-ROM and online distribution. An attempt to continue the floppy disk was the SuperDisk in the late 1990s, with a capacity of 120 megabytes and backward compatible with standard 3 or 1/2 inch floppies. A format war briefly occurred between SuperDisk and other high-density removable disk products, although ultimately flash memory, recordable CDs, DVDs, and online storage would render the matter moot. External USB-based floppy disk drives are still available. Many modern systems provide firmware support for booting from such a drive. Decline: mechanically incompatible higher-density disks were introduced, like the iOmega zip disk. Adoption was limited by the competition between proprietary formats and the need to buy expensive drives for computers where the disks would be used. In some cases, failure in market penetration was exacerbated by release of higher capacity versions of the drive and media not backward compatible with the original drives, dividing the users between new and old adopters. A chicken or the egg scenario ensued, with consumers wary of making costly investments into unproven and rapidly changing technologies, resulting in none of the technologies becoming an established standard. Apple introduced the iMac in 1998 with a CD-ROM drive but no floppy drive. This made USB-connected floppy drives popular accessories as the iMac came without any writable removable media device. This transition from standard floppies was relatively easy for Apple, since all Macintosh models originally designed to use a CD-ROM drive could boot and install their operating system from CD-ROM early on. Recordable CDs with even greater capacity, compatible with existing infrastructure of CD-ROM drives, made the new floppy technologies obsolete. The floppy disk's remaining reusability advantage was then eliminated by rewritable CDs. Networking, advancements in flash-based devices and widespread adoption of USB provided another alternative that in turn made both floppy disks and optical storage obsolete for some purposes. The rise of file sharing and multi-megapixel digital photography encouraged the use of files larger than most 3 or 1/2 inch disks could hold. Floppy disks were commonly used as sneakernet carriers for file transfer, but the broad availability of LANs and fast internet connections provided a simpler and faster method of transferring such files. Other removable storage devices have advantages in both capacity and performance when network connections are unavailable or when networks are inadequate. Use in the early 21st century. Nonetheless, as of 2002 most manufacturers still provided floppy disk drives as standard equipment to meet user demand for file transfer and an emergency boot device as well as the general secure feeling of having the familiar device. Subsequently, enabled by the widespread support for USB flash drives and BIOS boot, manufacturers and retailers progressively reduced the availability of floppy disk drives as standard equipment. In February 2003, Dell announced that floppy drives would no longer be pre-installed on Dell Dimension home computers, although they were still available as a selectable option and purchasable as an aftermarket OEM add-on. On January 29, 2007, PC World stated that only 2% of the computers they sold contained built-in floppy disk drives. Once present stocks were exhausted, no more standard floppies would be sold. In 2009, Hewlett-Packard stopped supplying standard floppy drives on business desktops. Floppy disks are used for emergency boots in aging systems lacking support for other bootable media, and for BIOS updates since most BIOS and firmware programs can still be executed from bootable floppy disks. If BIOS updates fail or become corrupt, floppy drives can sometimes be used to perform a recovery. The music and theater industries still use equipment requiring standard floppy disks. Industrial automation equipment such as programmable machinery and industrial robots may not have a USB interface. Data and programs are then loaded from disks, damageable in industrial environments. This may not be replaced due to cost or requirement for continuous availability. Existing software emulation and virtualization do not solve this problem because no operating system is present or a customized operating system is used that has no drivers for USB devices. Hardware floppy disk emulators can be made to interface floppy disk controllers to a USB port that can be used for flash drives. Corporate computer environments may still make use of floppy disks, for older machines that do not support the current company networks, and in the case of laptops where Wi-Fi is not considered secure. The floppy disk provides for a controlled means of file transfer by permitting only a few files to be transmitted. This is as USB ports on enterprise computer terminals workstations are often disabled in order to prevent employees from using a flash memory drive to take large amounts of data for unauthorized use. In addition, the loss of a floppy disk has less consequences than the loss of a flash drive. Legacy. For more than 2 decades, the floppy disk was the primary external writable storage device used. Most computing environments before the 1990s were non-networked and floppy disks were the primary means of transferring data between computers, a method known informally as sneakernet. Unlike hard disks, floppy disks are handled and seen. Even a novice user can identify a floppy disk. Because of these factors, a picture of a 3 1/2-inch floppy disk has become an interface metaphor for saving data. The floppy disk symbol is still used by software on user interface elements related to saving files, such as the release of Microsoft Office 2013, even though the physical floppy disks are largely obsolete. Design. Structure. The 5 1/4-inch disk has a large circular hole in the center for the drive spindle and a small oval aperture in both sides of the plastic to allow the drive's heads to read and write data. The magnetic medium can be spun by rotating it from the middle hole. A small notch on the right of the disk identifies that it is writable, detected by a mechanical switch or phototransistor above it. If it is not present, the disk is read-only. Punch devices were sold to convert read-only disks to writable ones and enable writing on the unused side of single-sided disks. Such modified disks became known as floppy disks. Tape may be used over the notch to protect writable disks from unwanted writing. This arrangement was the converse of the system used on 8-inch floppy disks where the notch had to be covered before the disk could be written to. Another LED phototransistor pair located near the center of the disk detects the index hole once per rotation in the magnetic disk. It is used to detect the angular start of each track and whether or not the disk is rotating at the correct speed. Early 8 1/2-inch and 5 1/4-inch disks had physical holes for each sector and were termed hard-sectored disks. Later soft-sectored disks had only one index hole, and sector position was determined by the disk controller or low-level software from patterns marking the start of a sector. Generally, the same drives were used to read and write both types of disks, with only the disks and disk controllers differing. Some operating systems utilizing soft sectors, such as Apple DOS, did not use the index hole. The drives designed for such systems often lacked the corresponding sensor. This was mainly a hardware cost-saving measure. Inside the disk are 2 layers of fabric, with the medium sandwiched in the middle. The fabric is designed to reduce friction between the medium and the outer casing, and catch particles of debris abraded off the disk to keep them from accumulating on the heads. The outer casing is usually a one-part sheet, double-folded with flaps glued or spot-welded together. The 8-inch disk had read-only logic that was the reverse of the 5 1/4-inch disk, with the slot on the side having to be taped over to allow writing. The core of the 3 1/2-inch disk is the same as the other 2 disks, but the front has only a label and a small aperture for reading and writing data, protected by the slider a spring-loaded metal or plastic cover, pushed to the side on entry into the drive. Rather than having a hole in the center, it has a metal hub which mates to the spindle of the drive. Typical 3 1/2-inch disk magnetic coating materials are DD2AA micrometer magnetic iron oxide, HD, 1.2AA micrometer cobalt-doped iron oxide, ED, 3AA micrometer barium ferrite. 2 holes at the bottom left and right indicate whether the disk is write protected and whether it is high density. These holes are spaced as far apart as the holes in punched A4 paper, allowing write-protected high-density floppies to be clipped into standard ring binders. A notch at top right ensures that the disk is in the correct orientation and an arrow at top left indicating direction of insertion. The drive usually has a button that when pressed ejects the disk with varying degrees of force, the discrepancy due to the ejection force provided by the spring of the slider cover. In IBM PC compatibles, a floppy disk may be inserted or ejected manually at any time. The drive has a change switch that detects when a disk is ejected or inserted. Failure of this mechanical switch is a common source of disk corruption if a disk is changed and the drive fails to notice. One of the chief usability problems of the floppy disk is its vulnerability. Even inside a closed plastic housing, the disk medium is highly sensitive to dust, condensation and temperature extremes. As with all magnetic storage, it is vulnerable to magnetic fields. Blank disks have been distributed with an extensive set of warnings, cautioning the user not to expose it to dangerous conditions. Disks must not be roughly treated or removed from the drive while the magnetic media is still spinning, since doing so is likely to cause damage to the disk, drive head, or stored data. On the other hand, the 301/2 floppy has been lauded for its mechanical usability by HCI expert Donald Norman. A simple example of a good design is the 301/2 magnetic diskette for computers, a small circular floppy magnetic material encased in hard plastic. Earlier types of floppy disks did not have this plastic case, which protects the magnetic material from abuse and damage. A sliding metal cover protects the delicate magnetic surface when the diskette is not in use and automatically opens when the diskette is inserted into the computer. The diskette has a square shape. There are apparently 8 possible ways to insert it into the machine, only one of which is correct. What happens if I do it wrong? I try inserting the disk sideways. The designer thought of that. A little study shows that the case really isn't square, it's rectangular, so you can't insert a longer side. I try backward. The diskette goes in only part of the way. Small protrusions, indentations, and cutouts prevent the diskette from being inserted backward or upside down. Of the 8 ways one might try to insert the diskette, only one is correct, and only that one will fit. An excellent design. Operation. A spindle motor in the drive rotates the magnetic medium at a certain speed, while a stepper motor-operated mechanism moves the magnetic read-write head, S, along the surface of the disk. Both read and write operations require the media to be rotating and the head to contact the disk media, an action accomplished by a disk load solenoid. To write data, current is sent through a coil in the head as the media rotates. The head's magnetic field aligns the magnetic particles directly below the head on the media. When the current is reversed, the particles align in the opposite direction, encoding the data digitally. To read data, the magnetic particles in the media induce a tiny voltage in the head coil as they pass under it. This small signal is amplified and sent to the floppy disk controller, which converts the streams of pulses from the media into data, checks it for errors, and sends it to the host computer system. A blank unformatted diskette has a coating of magnetic oxide with no magnetic order to the particles. During formatting, the particles are aligned, forming a pattern of magnetized tracks, each broken up into sectors, enabling the controller to properly read and write data. The tracks are concentric rings around the center, with spaces between tracks where no data is written. Gaps with padding bytes are provided between the sectors and at the end of the track to allow for slight speed variations in the disk drive, and to permit better interoperability with disk drives connected to other similar systems. Each sector of data has a header that identifies the sector location on the disk. A cyclic redundancy check is written into the sector headers and at the end of the user data so that the disk controller can detect potential errors. Some errors are soft and can be resolved by automatically retrying the read operation. Other errors are permanent and the disk controller will signal a failure to the operating system if multiple attempts to read the data still fail. After a disk is inserted, a catch or lever at the front of the drive is manually lowered to prevent the disk from accidentally emerging, engage the spindle clamping hub, and in two-sided drives, engage the second read-write head with the media. In some 5 or 1/4-inch drives, insertion of the disk compresses and locks an ejection spring which partially ejects the disk upon opening the catch or lever. This enables a smaller concave area for the thumb and fingers to grasp the disk during removal. Newer 5 or 1/4-inch drives and all 3 or 1/2-inch drives automatically engage the spindle and heads when a disk is inserted, doing the opposite with the press of the eject button. On Apple Macintosh computers with built-in floppy drives, the ejection button is replaced by software controlling an eject motor which only does so when the operating system no longer needs to access the drive. The user could drag the image of the floppy drive to the trash can on the desktop to eject the disk. In the case of a power failure or drive malfunction, a loaded disk can be removed manually by inserting a straightened paper clip into a small hole at the drive's front panel, just as one would do with a CD-ROM drive in a similar situation. Sizes. Different sizes of floppy disks are mechanically incompatible, and disks can fit only one size of drive. Drives with 3 or 1/2-inch and 5 or 1/4-inch slots were available during the transition period between the sizes, but they contain 2 separate drive mechanisms. In addition, there are many subtle, usually software-driven incompatibilities between the two. 5 or 1/4-inch disks formatted for use with Apple II computers would be unreadable and treated as unformatted on a Commodore. As computer platforms began to form, attempts were made at interchangeability. For example, the SuperDrive included from the Macintosh SE to the Power Macintosh G3 could read, write and format IBM PC format 3 or 1/2-inch disks, but few IBM-compatible computers had drives that did the reverse. 8-inch, 5 or 1/4-inch and 3 or 1/2-inch drives were manufactured in a variety of sizes, most to fit standardized drive bays. Alongside the common disk sizes were non-classical sizes for specialized systems. 8-inch floppy disk. The first floppy disk was 8 inches in diameter, and was protected by a flexible plastic jacket. IBM used this size as a way of loading microcode into mainframe processors, and the original 8-inch disk was not field-writable. Rewritable disks and drives became useful. Early microcomputers used for engineering, business, or word processing often used 1 or more 8-inch disk drives for removable storage. The CP/M operating system was developed for microcomputers with 8-inch drives. An 8-inch disk could store about a megabyte. Many microcomputer applications didn't need that much capacity on one disk, so a smaller size disk with lower cost media and drives was feasible. The 5 or 1/4-inch drive succeeded the 8-inch size in many applications, and developed to about the same storage capacity as the original 8-inch size, using higher density media and recording techniques. 5 or 1/4-inch floppy disk. The head gap of an 80 Euro track high-density 5 or 1/4 Euro-inch drive is smaller than that of a 40 Euro track double-density drive but can format, read and write 40 Euro track disks well provided the controller supports double-stepping or has a switch to do such a process. A blank 40 Euro track disk formatted and written on an 80 Euro track drive can be taken to its native drive without problems, and a disk formatted on a 40 Euro track drive can be used on an 80 Euro track drive. Disks written on a 40 Euro track drive and then updated on an 80 track drive become unreadable on any 40 Euro track drives due to track width incompatibility. Single-sided disks were coated on both sides, despite the availability of more expensive double-sided disks. The reason usually given for the higher cost was that double-sided disks were certified error-free on both sides of the media. Architectural differences among computer platforms negated this claim, however, with Radio Shack TRS-80 Model I computers using one side and the Apple II machines the other. Double-sided disks could be used in drives for single-sided disks, one side at a time, by turning them over. More expensive dual-head drives which could read both sides without turning over were later produced, and eventually became used universally. 3 or 1/2-inch floppy disk. In the early 1980s, a number of manufacturers introduced smaller floppy drives and media in various formats. A consortium of 21 companies eventually settled on a 3 or 1/2-inch floppy disk also known as microdiskette, microdisk, or microfloppy, similar to a Sony design, but improved to support both single-sided and double-sided media, with formatted capacities of 360 kilobytes and 720 kilobytes respectively. Single-sided drives shipped in 1983, and double-sided in 1984. What became the most common format, the double-sided, high-density 1.44 MB disk drive, shipped in 1986. The first Macintosh computers used single-sided 3.5-inch floppy disks, but with 400 kilobytes formatted capacity. These were followed in 1986 by double-sided 800 kilobytes floppies. The higher capacity was achieved at the same recording density by varying the disk rotation speed with arm position so that the linear speed of the head was closer to constant. Later Macs could also read and write 1.44 MB HD disks in PC format with fixed rotation speed. All 3.5-inch disks have a rectangular hole in one corner which, if obstructed, write-enable the disk. The HD 1.44 MB disks have a second, unobstructed hole in the opposite corner which identifies them as being of that capacity. In IBM-compatible PCs, the three densities of 3.5-inch floppy disks are backwards compatible. Higher density drives can read, write and format lower density media. It is physically possible to format a disk at the wrong density, although the resulting disk will not work properly. Fresh disks manufactured as high density can theoretically be formatted at double density only if no information has been written on the disk in high density, or the disk has been thoroughly demagnetized with a bulk eraser, as the magnetic strength of a high-density record is stronger and overrides lower density, remaining on the disk and causing problems. Writing at different densities than disks were intended for, sometimes by altering or drilling holes, was possible but deprecated. The holes on the right side of a 3.5-inch disk can be altered as to make some disk drives and operating systems treat the disk as one of higher or lower density, for bidirectional compatibility or economical reasons. Some computers, such as the PS/2 and Acorn Archimedes, ignore these holes altogether. It is possible to make a 3.5-inch floppy disk drive be recognized by a system as a 5.25-inch 360 kilobytes or 1200 kilobytes drive, and to read and write disks with the same number of tracks and sectors as those disks. This had some application in data exchange with obsolete CP/M systems. Other sizes. Other smaller floppy size were proposed, especially for portable or pocket-sized devices that needed a smaller storage device. 3-inch disks similar in construction to 3.5-inch were manufactured and used for a time, particularly by Amstrad computers and word processors. A 2-inch nominal size was introduced for compact pocket computers and was used with some electronic musical instrument controllers. Neither of these sizes became popular in personal computers. Sizes, performance and capacity. Floppy disk size is often referred to in inches, even in countries using metric and though the size is defined in metric. The ANSI specification of 3.5-inch disks is entitled in part 90 mm though 90 mm is closer to 3.54 inches. Formatted capacities are generally set in terms of kilobytes and megabytes. Data is generally written to floppy disks in sectors and tracks. For example, the HD format of 3.5-inch floppy disks uses 512 bytes per sector, 18 sectors per track, 80 tracks per side and 2 sides, for a total of 1,474,560 bytes per disk. Some disk controllers can vary these parameters at the user's request, increasing storage on the disk, although they may not be able to be read on machines with other controllers. For example, Microsoft applications were often distributed on 3.5-inch 1.68 megabytes DMF disks formatted with 21 sectors instead of 18. They could still be recognized by a standard controller. On the IBM PC, MSX and most other microcomputer platforms, disks were written using a constant angular velocity format, with the disk spinning at a constant speed and the sectors hold the same amount of information on each track regardless of radial location. This was not the most efficient way to use the disk surface with available drive electronics. Because the sectors have constant angular size, The 512 bytes in each sector are compressed more near the disk center. A more space-efficient technique would be to increase the number of sectors per track toward the outer edge of the disk, from 18 to 30 for instance, thereby keeping constant the amount of physical disk space used for storing each sector. An example is zone bit recording. Apple implemented this in early Macintosh computers by spinning the disk slower when the head was at the edge, while maintaining the data rate, allowing 400 kilobytes of storage per side and an extra 160 kilobytes on a double-sided disk. This higher capacity came with a disadvantage: the format used a unique drive mechanism and control circuitry, meaning that Mac disks could not be read on other computers. Apple eventually reverted to constant angular velocity on HD floppy disks with their later machines, still unique to Apple as they supported the older variable speed formats. Disk formatting is usually done by a utility program supplied by the computer OS manufacturer. Generally, it sets up a file storage directory system on the disk, and initializes its sectors and tracks. Areas of the disk unusable for storage due to flaws can be locked so that the operating system does not attempt to use them. This was time-consuming, so many environments had quick formatting which skipped the error-checking process. When floppy disks were often used, disks pre-formatted for popular computers were sold. A formatted floppy disk does not include the sector and track headings of an unformatted disk. The difference in storage between them depends on the drive's application. Floppy disk drive and media manufacturers specify the unformatted capacity. It is implied that this should not be exceeded, since doing so will most likely result in performance problems. DMF was introduced permitting 1.68 megabytes to fit onto an otherwise standard 3 or 1/2 inch disk. Utilities then appeared allowing disks to be formatted as such. Mixtures of decimal prefixes and binary sector sizes require care to properly calculate total capacity. Whereas semiconductor memory naturally favors powers of 2, the capacity of a disk drive is the product of sector size, sectors per track, tracks per side and sides. Although other sector sizes have been known in the past, formatted sector sizes are now almost always set to powers of 2, and, in some cases, disk capacity is calculated as multiples of the sector size rather than in just bytes, leading to a combination of decimal multiples of sectors and binary sector sizes. For example, 1.44 MB 3 or 1/2 inch HD disks have the M prefix peculiar to their context, coming from their capacity of 2,885 byte sectors, inconsistent with either a decimal megabyte nor a binary megabyte. Hence, these disks hold 1.47 MB or 1.41 MB. Usable data capacity is a function of the disk format used, which in turn is determined by the FDD controller and its settings. Differences between such formats can result in capacities ranging from approximately 1300 to 1760 kb on a standard 3 or 1/2 inch high-density floppy. The highest capacity techniques require much tighter matching of drive head geometry between drives, something not always possible and unreliable. For example, the LS240 drive supports a 32 MB capacity on standard 3 or 1/2 inch HD disks, but it is, however, a write-once technique, and requires its own drive. The raw maximum transfer rate of 3 or 1/2 inch HD floppy drives and interfaces, disregarding overheads, is as much as 1000 kilobits s, or approximately 83% that of single-speed GDA Euro-ROM. This represents the speed of raw data bits moving under the read head. However, because of the very high amount of overhead in the system, the actual user data read-write speed is much lower. In fact, a DSHD diskette formatted with an efficient non-sequential sector layout could sync and read an average of only slightly more than 3 double-sided pairs of 512 Eurobyte sectors per 0.2s revolution, or a little over 15 sectors second, for an effective data rate of approximately 125 kbits. At this speed, a single, disk-filling file would take a good 90 seconds to transfer. Smaller or fragmented files further reduce transfer speed because of the slow head seek speed and the requirement to reread the FAT from track 0 along with any folder data, as removable media is rarely cached. Unusually, when compared to hard disks, optical drives and archive tapes, the floppy disk standard proper did not receive any further successful speed or capacity upgrades throughout its period of relevance, from the mid-80s introduction of DSHD through to its eventual abandonment more than 20 years later. However, some developments did seek to improve this, but with limited success. Double-sided extended density 3.5-inch floppy disks, introduced by Toshiba in 1987 and adopted by IBM on the PS/2 in 1994, doubled the number of sectors per track, thereby providing double the data rate and capacity of conventional DSHD 3.5-inch drives. Although it was not enabled by default, both the MSA Euro DOS/Windows 3.1 Smart Drive Caching TSAT and the System Cache of later Windows versions can be configured to cache removable drives, including floppy disks. Similarly, some USB floppy drives use caching to increase performance while being built from standard speed drives. Alternatively, the X10 accelerated floppy drive was an attempt to physically increase floppy performance by increasing spindle RPM. More successfully, a number of tape-based backup drives that interfaced via the floppy drive controller were developed and sold by manufacturers such as Travan and Iomega. These made better use of the available bandwidth, and eventually pushed the 500's limits of standard motherboard floppy disk controllers. Higher-end models could make use of the 2000 kbits throughput of DSED controllers, and plug-and high-speed adapter cards were offered for PCs lacking this capability. Though inadequate by modern standards, their speed was competitive with early CD recorders and zip drives, and was sufficient for overnight backups of a contemporary home or small office user's hard drive. See also: DD, disk image, don't copy that floppy, semi-virtual diskette, references. Bibliography, Weyrich, Stephen. The Disk 2, a detailed essay describing one of the first commercial floppy disk drives. Immers, Richard. Neufeld, Gerald G. Inside Commodore DOS, a Eurocent, the complete guide to the 1541 disk operating system. Datamost and Reston Publishing Company. ISBN 0-8359-3091-2. English, Lithha. Skrzyfnowski, Norbert. The Anatomy of the 1541 Disk Drive. Grand Rapids, Michigan, USA, Abacus Software. ISBN 0-916439-01-1. Hewlett-Packard, 9121 DS Disk Memory Operators Manual. Printed September 1, 1982. Part number 09121-90000. External links, Programming Floppy Disk Controllers, How Stuff Works, How Floppy Disk Drives Work, Computer Hope, Information about Computer Floppy Drives, NCITS, Tech Information on Floppy Disks Drives and Media, Floppy Disk Drives and Media Technical Information, The Floppy User Guide Historical Technical Material.